when a massive thunderstorm rolls in, there's always that split second that just completely messes with your head.
Oh, yeah. The delay.
Right. You're sitting on your porch, looking out at the horizon, and you see this violent, jagged flash of lightning light up the entire sky. But it is completely silent.
Oh.
The world is just quiet. And then you wait.
Just waiting for it to catch up.
Exactly. 1 second, 2 seconds, 3, and then bam, the thunder finally hits you and rattles your window.
It's actually the perfect everyday example of information delay. I mean, the physical event itself, the actual lightning strike already happened out there in the world. But your senses, your eyes and your ears, they're processing the reality of that event on completely different timelines.
Right. Your eyes are screaming, it's happening right now.
Yeah.
But your ears are essentially living in the past, just waiting for the news to arrive. It's a total sensory disconnect.
Yeah, it really is.
But what if that same kind of disconnect, that exact same gap between a physical event and the information arriving about the event, was hiding at the very foundation of modern physics? Welcome to The Deep Dive. I'm your host.
And I'm your resident technical guide for today.
Today, we are bringing you a fascinating, highly visual challenge to one of the most famous physicists in history, Albert Einstein. We're jumping right into this.
We really are. So we're looking at a deeply technical, incredibly unique piece of source material today. It's a blog post titled Draft, Einstein Slacking 131. And what makes this so compelling is that the author isn't just throwing complex algebraic equations at us.
Thank goodness for that.
Right. Instead, they're using a 3D modeling software called Blender to construct this purely geometric spatial critique of special relativity and the historical Michelson-Morley experiment.
And the mission for our deep dive today is to really visualize this alternative framework. The author argues that a foundational concept in physics, something called Lorentz contraction, isn't actually a physical reality. They argue it's just a mathematical patch. Like a conceptual Band-Aid used to cover up a massive geometric oversight early in the history of science.
Which is a huge claim.
It's massive. Now, to be incredibly clear right out of the gate, we are not here to take sides. We aren't endorsing a new controversial theory of physics, and we certainly aren't claiming Einstein was wrong. We are just here to impartially explore this author's incredibly spatial, three-dimensional way of visualizing light, time, and moving objects. It's a wild thought experiment. Okay, let's unpack this.
To really grasp the author's argument, we have to start by, well, throwing out the chalkboard map and stepping inside a 3D blueprint.
Okay, I'm picturing it.
Picture the digital space inside that modeling software, Blender. The author models a massive 20 by 20 by 20 cube representing a train carriage or the housing of a scientific instrument.
But it's not a solid box, right?
No, it's not a solid, opaque box. Imagine a giant floating digital cage constructed entirely out of thousands of tiny individual glowing spheres. Each one has a radius of just 0.2.
Okay, so it's like a massive grid of glowing marbles suspended in the dark.
That's exactly the visual. And this is where the author introduces a core philosophical distinction that drives their entire critique. They separate reality into two distinct perspectives, the God's eye view and the camera eye view.
Let me stop you there, because those names sound a bit, dramatic. God's eye view just means actual reality, right? Why give it a special title?
Well, because in theoretical physics, separating objective reality from our observation of it is actually incredibly difficult. In the God's eye view, which corresponds to a standard Cartesian 3D space with an XYZ grid, every single glowing marble in that cube exists simultaneously.
Okay.
If you have the God's eye, you aren't constrained by the speed of light. You just see the raw, objective physical space exactly as it is, all at once.
But we don't have that view. None of our scientific instruments have that view. We're totally constrained. We just have the camera eye.
Which changes everything. Imagine placing a digital camera somewhere outside that giant cube of marbles. Let's say down at coordinates y equals -40, z equals 20, looking up at it.
Got it.
The author points out a crucial geometric reality. Imagine a transparent sphere of radius 1 around this camera eye. For you to see a complete image of that entire cube at a specific moment, say, exactly 12.000 p.m. light rays from all those different little glowing marbles have to hit that sphere around your camera eye at the exact same time.
Wait, hold on. If I'm looking at a giant 20 by 20 cube, The marbles at the back of the cube are significantly farther away from my camera than the marbles at the front.
Exactly. Which means for the light from the back of the cube to arrive at your lens at the exact same millisecond as the light from the front.
The light from the back had to leave earlier.
Yes.
The light rays had to depart from those different marbles at totally different, scattered times in the past.
That is the crucial insight. For the information to arrive at your camera eye simultaneously, it had to depart sequentially.
Oh, wow. That is just like looking up at a starry night sky. You know, you go out on a clear night and your camera eye sees this beautiful, cohesive dome of stars, all existing right now in your field of vision.
Right.
But you're actually looking at a massive patchwork of ghosts. Like that bright star over there is what it looked like 10 years ago, and that faint star over there is 1,000,000 years ago. Your brain just stitches 1,000,000 different pasts together into a single present image.
And if we connect this to the bigger picture, the author's entire argument hinges on the idea that early physicists accidentally confused these two views. The claim is that they treated the delayed patchwork camera eye observation as if it were the instantaneous God's eye physical reality.
Okay, but if this camera eye delay is so painfully obvious when we look at the stars, why didn't the founding fathers of physics account for it when they built their theories of motion? Surely they knew light took time to travel.
They did know, but applying it to moving objects gets incredibly messy. This delay in light doesn't just mess with when we see things. If we're standing on a moving object, this delay dramatically alters the apparent speed and the angle at which we see things move.
Okay, how so?
Well, the source takes us back in time to an astronomer named James Bradley to prove this point.
Okay, set the scene for me. What was Bradley looking at?
Bradley was studying starlight. He created a model to understand how we observe stars from a moving Earth. Imagine the Earth moving horizontally along the x-axis, while light from a star drops straight down the z-axis at the speed of light, like 1.0 c.
Okay, I'm with you.
Because the Earth is moving across the light's downward path, the starlight develops an apparent velocity from the perspective of the astronomer.
Oh, this is exactly like driving in a heavy rainstorm.
Yes.
If you're parked, the rain is just falling straight down on your roof. But the second you accelerate onto the highway, the rain looks like it's slamming into your windshield at this harsh, slanted angle. The rain hasn't changed direction, but your motion warps the angle at which you experience it.
That's a perfect analogy. If the Earth is moving horizontally at, say, 60% of the speed of light, so 0.66 a, the math shows that the starlight appears to be traveling at a slanted angle with an artificially higher apparent speed, like 1.166 c. Bradley realized that to actually catch this starlight down the tube of his telescope, he couldn't point it straight up in the star.
You had to tilt it.
Right, he had to physically tilt his telescope forward to adjust for the apparent angle caused by the Earth's motion.
Okay, so Bradley clearly understood that motion warps observation. He tilted the telescope. He compensated for the rain on the windshield. So what went wrong? Where is the historical misstep?
That brings us to the famous physicist Albert Michelson and his foundational 1881 experiment. And a quick historical note from the source, Michelson did this first experiment alone. His famous partner, Edward Morley, didn't actually join him until the 1887 re-experiment.
Oh, interesting. I always just hear Michelson-Morley.
Right, so Michelson built a device called an interferometer to measure the speed of light.
And according to the author, Michelson made a massive assumption when he set this device up.
Yeah, the author models Michelson's setup inside that 3D blender space. Michelson placed his device inside what the author calls a train representing the Earth moving through the external electromagnetic field.
Okay, so we're on a train.
Let's use that same speed. The train is moving forward at 0.6 c. Michelson assumed that if he fired a beam of light sideways perpendicular to the train's forward movement, so in the y plane, that the sideways light would just behave normally, tracing a perfect symmetrical path.
Let me pause you right there, because this is where physics always loses me. If I am inside a moving train and I bounce a tennis ball off the wall, it behaves normally. Why wouldn't light?
Because the tennis ball is a physical object that inherits the momentum of the moving train. It's sharing your physical space. But light doesn't work like a tennis ball. The author compares light to the sound of a siren on a moving ambulance.
Okay.
The sound wave, or the light wave, travels through an external medium, in this case, the electromagnetic field.
Oh, I see. So when you flash a beam of light inside the train, the light doesn't get a free speed boost from the train's engines. It answers to the external field outside the train, not the floorboards beneath your feet.
That is the crux of it. Because the light is governed by the external field, the author's math calculates that inside this moving train, the apparent speed of light is warped in all directions.
Warped how?
If the train is rushing forward at point 6c, the apparent speed of a light beam trying to move forward along the x-axis is severely reduced to just point 4c because the front of the train is running away from it.
Oh.
But if you measure light traveling sideways, its apparent speed is entirely different. It's point 8c.
Here's where it gets really interesting. Because if the apparent speed of light inside the train is sluggish in the forward direction, but much faster in the sideways direction, then Michelson's entire baseline for measuring light was broken from the very beginning.
Exactly.
He was expecting the light to trace a neat, perfectly symmetrical path. But the actual geometry of the observation, if you account for the camera eye in the moving train, was completely stretched out and distorted.
And to really prove just how violently warped this internal geometry gets, the author designs an ultimate thought experiment. We are going back inside that massive moving subway train, and we're going to throw what the author calls photon balls.
Okay, put me inside this situation. I'm standing in the exact dead center of this massive 20 by 20 by 20 subway car. The driver's cabin is straight ahead of me, 10 units away on the x-axis.
You're standing there, and the train is rocketing forward through the electromagnetic field at point 6c. You decide to pitch a photon ball toward the driver's cabin, but you don't throw it straight ahead. The author specifies that you throw it at a steep upward diagonal angle, specifically a 56.31 degree angle.
Wait, 56.31 degrees. Why diagonally? If I want to see how long it takes light to reach the driver, why wouldn't I just chuck the photon ball straight at the back of his seat? What does a steep upward angle prove?
Well, throwing it straight only tests one dimension. By throwing it at a harsh upward angle, which is a ratio of 0.8 vertical to 0.6 horizontal, it forces us to track two dimensions of travel simultaneously. You have the horizontal movement toward the driver and the vertical movement toward the ceiling, all while the train itself is moving.
Ah, okay. It exposes the distortion.
Exactly. So you throw the light diagonally toward the ceiling above the driver. What happens?
Well, normally I would think the ball travels forward, it travels upward, and it smacks into the wall right above the driver a fraction of a millisecond later. Boom. Done.
But the train is moving. Because the subway car is plowing through the external field at point 6c, the driver's seat is literally running away from the light you just threw.
Like trying to run forward on one of those moving airport walkways that is going in the opposite direction. You're pumping your legs, but the end of the walkway just keeps escaping you.
Exactly that. The photon ball is trying to move forward to hit the wall, but from the perspective of the moving train, its apparent horizontal speed chasing the driver is drastically reduced. It's only 0.36c.
Oh, man.
It's barely creeping up on the driver's cabin. According to the author's calculations, it takes an agonizing amount of time for the light to finally catch up. In this scaled model, it takes a massive 27.77 seconds for the light to hit the back wall of the driver's cabin.
Let me get this straight. In a normal stationary room, light hits the wall before my brain can even register it. It's instantaneous.
Right.
But here, because the front wall of the train is constantly running away through the external field, the light takes almost 30 seconds to make contact. The entire shape of reality inside that train is stretching like a rubber band.
The geometry is entirely stretched. And remember, during that massive delay, the photon ball doesn't just pause in midair. It's continuing to travel outward and upward along that steep diagonal angle. It spends all that extra 27.77 seconds climbing higher and higher toward the ceiling.
So when it finally slams into the wall behind the driver, nearly half a minute later, it hits way, way higher on the wall than you would ever expect if you were just standing in the stationary room.
Considerably higher. Let's say you threw it at a normal 45-degree angle. You'd expect it to hit the wall at a height of 14.1 on the z-axis. But because of the delay, it hits much higher.
Wow.
And if you fired a whole ring of these photon balls at that same upward angle, the author calculates that it creates a massive circular trace on the wall. The radius of that circle is 17.728 on the wall, or 22.16 from the perspective of the external field.
That is just, it's mind-boggling. The internal geometry, the literal path the light takes from your hand to the walls of the train, is completely pulled apart and warped by the movement of the train through the external field.
Completely warped.
So what does this all mean? We have this incredibly messy, stretched out, delayed, funhouse mirror reality inside the moving train, where light seems to travel at different apparent speeds depending on which direction you throw it. How did the brilliant minds of modern physics deal with this massive headache?
This brings us to the author's ultimate punchline. According to the source, the physicist Hendrik Lorentz encountered these exact same messy calculations. He saw that the apparent speed of light was not constant in all directions when observed from a moving platform.
Okay.
But instead of accepting this delayed, highly distorted geometry of the camera eye, instead of accepting that our observation of light is inherently warped by our own motion, he invented something called Lorentz contraction.
Lorentz contraction.
Yeah.
The mind-bending idea that moving objects physically shrink in the direction of their motion.
What's fascinating here is that the author views Lorentz contraction not as a true, literal physical phenomenon, but as a patch, a computational trick, a mathematical band-aid.
It's like a software developer finding a massive bug in their code that breaks all the visuals, and instead of carrying the code down and fixing the underlying engine, they just write a quick script to hide the error message so the program keeps running.
That is the exact accusation. The author argues that Lorentz, and later Einstein with a concept called Minkowski spacetime, essentially force the equations to balance perfectly.
How so?
To explain it simply, Minkowski spacetime is the mathematical grid used in modern physics that combines three-dimensional space and time into a single interlocking stage. On this stage, the speed of light is the ultimate speed limit, and it must measure as constant in all directions for an observer on a train.
Right. That's like rule number one of relativity.
Exactly. But to make that math work seamlessly on paper, to keep the light constant despite the train's movement, the physical space itself had to be mathematically compressed. The train had to shrink.
The author is basically calling this out as a grand illusion. They believe that thinking light acts perfectly normally, constantly and symmetrically inside a moving train is a complete fantasy. The early physicists, in this view, failed to properly separate the instantaneous God's eye reality from the delayed camera eye observation.
Yeah, that's the core of it.
They confused the finite 3D space where things are actually happening all at once with the delayed, scattered information arriving sequentially to the observer.
Think about the implications of that. Because they took the warped, delayed photograph of reality and mistook it for the physical reality itself, they had to invent a warped physics, like physical objects magically shrinking and time literally slowing down just to explain the distortions in the photograph. It's a profound structural critique of the entire sequence of physical reasoning that led to special relativity.
It really is a wild, counterintuitive journey to wrap your head around. I mean, we started with the simple digital 3D cube in Blender made of glowing spheres, just realizing that observing something means waiting for the light to arrive. Then we followed James Bradley tilting his telescope in the rain, proving that moving through space completely warps the apparent angle of incoming light.
We then placed Albert Michelson's instruments inside a moving train, highlighting how his expectation of perfectly symmetrical light paths was a flawed baseline.
And then we put you, the listener, right in the center of that runaway subway car, throwing photon balls diagonally at the ceiling. We watched the geometry of that room stretch so violently that it takes light an agonizing 27 seconds to hit a wall that's just a few feet away.
It's a crazy visual.
It really is. And all of this building to the author's central, controversial claim that the messy, raw geometry of light delay was swept under the rug, and the shrinking trains of Lorentz contraction were invented as a mere mathematical patch to cover it up.
And to you, the listener, I want to emphasize that whether or not you believe this single blog post successfully overturns over a century of established, thoroughly tested relativistic physics isn't necessarily the point of studying it.
No, definitely not.
The true value here is the intense mental exercise. It forces us to actively visualize the profound difference between the actual objective universe taking place around us and the inherently delayed, heavily distorted image of the universe that our biological camera eyes and our mathematical models actually receive. It demands that we rigorously question our deepest assumptions about what observation truly is.
It makes you realize how entirely dependent our grasp of reality is on the sheer speed of information. Which leaves us with a pretty provocative final thought to send you off with.
Oh, what's that?
Think back to that thunderstorm we talked about at the very beginning of the deep dive. The silent lightning and the delayed crash of the thunder. If, as this author allegedly claims, brilliant physicists had to invent a mathematical patch just to reconcile how we observe light with how physical space actually exists.
Hey, let me rephrase that. If they had to invent a patch just to make the math work, what other fundamental laws of our universe might just be illusion?
Oh, wow, that is a deep thought. Are there other core, unquestionable truths about our reality that are actually just artifacts created by the limited processing speed of our own biological camera eyes? Could our entire subjective feeling of now, this exact present moment you're experiencing, be nothing more than a localized trick of the light, something to mull over? Until next time.